Imagine that you have achieved humanity's most audacious dream, and now you are inside a spaceship capable of reaching speeds that defy everything we know. You feel the acceleration pushing your body against the seat as the stars begin to turn into bright lines through the observation window. Your heart races with the excitement of knowing that you are about to experience something that no human being has ever experienced. You are approaching the speed of light, and you can barely contain the euphoria of imagining the distant worlds you can visit, the galaxies you can contemplate from near, the cosmic wonders that will unfold before your amazed eyes. But there is something that no one has told you. There is a terrifying truth hidden in the equations of physics that is about to completely destroy your understanding of reality. Because when you finally return from this epic trip at the speed of light, when your ship lands back on Earth's soil, and you take those first eager steps to hug your family and tell them about the wonders you have witnessed, you will discover something that will chill your blood and make your world fall apart in an instant. Everyone you loved, everyone you knew, every person who was part of your life will be dead. Not just dead, but dead for centuries, perhaps millennia. Their bones will have turned to dust. Their names will have been forgotten by history. The civilization you left behind may have flourished and collapsed dozens of times during what to you seemed like just a few months or years of travel. And this is not science fiction. This is not dramatic exaggeration. This is not philosophical speculation. This is pure physics, proven, demonstrated mathematically and confirmed experimentally. And that's exactly what astrophysicist Neil deGrasse Tyson brilliantly explained when asked what would really happen if someone traveled at the speed of light. And if you're like me, someone completely fascinated by the deepest mysteries of the universe and the truths that challenge our intuition about reality, then subscribe to the channel now, because this journey we're about to take together will literally rebuild the way you understand time, space, and your own existence. And I need you to be with me until the end, because the explanations that will come in the next explanations are progressively more impressive, and the conclusion will leave your mind completely expanded. So let's dive into this ocean of cosmic knowledge and discover why the speed of light takes such a devastating toll on anyone who dares to challenge it. It all starts with a seemingly simple question that a 16-year-old young man asked himself while walking through the streets of a Swiss city at the end of the 19th century. This young man was called Albert Einstein, and the question that consumed his teenage mind was deceptively basic. What would happen if I could ride a beam of light? If I could move alongside a beam of light at the same speed as it? What would I see? This seemingly naive question would take a whole decade to answer. And when Einstein finally found the answer in 1905, he realized that he had discovered something that would forever change our understanding of the cosmos. The answer was both simple and devastating. You cannot ride a beam of light because light will always move at 200,000 kilometers per second relative to you, no matter how fast you are moving. No matter whether you are standing still or traveling at 99% the speed of light, when you measure the speed of a light beam, it will always be moving away from you at exactly 300,000 kilometers per second. That seems impossible. It seems to violate every basic logic that we have learned since childhood. If you are in a car going 100 kilometers per hour and another car passes you at 120 kilometers per hour, it appears to be moving at only 20 kilometers per hour relative to you. We subtract speeds all the time, and this works perfectly in the everyday world. But with light, the rules are completely different. And Einstein realized that the only way to resolve this apparent paradox was to accept a revolutionary truth. If the speed of light is always constant for all observers, then something else needs to change to accommodate this constancy. And that something else is none other than time itself. Time is not absolute. Time does not flow the same way for everyone. Time is flexible, malleable, relative, and the faster you move through of space, the slower you move through time. This is the essence of time dilation, and it is exactly the mechanism that will cause everyone you love to be dead when you return from a journey close to the speed of light. But let's understand this deeply because the details are even more fascinating than the overall concept. Neil deGrasse Tyson often uses a brilliant analogy to explain why this happens. Imagine you have a fixed speed budget through space-time. You can use that budget to move through space or to move through time, but the sum total always needs to remain constant. When you are sitting completely still reading this script, you are not moving at all through space, but you are using your entire speed budget to move through time. That's why that time passes normally for you at this moment. You are traveling through time at the maximum possible speed. Now imagine that you start walking. A small fraction of your speed budget has been diverted to spatial movement, which means that there is slightly less left for temporal movement. Time passes a tiny bit slower for you as you walk than when you were standing still. Of course, this effect is so microscopically small at normal human speeds that it is completely imperceptible, but it exists. It has been measured. It is happening right now. Now imagine that you speed up to 10%. At 100% the speed of light, a significant fraction of your speed budget is now devoted to space movement. Time begins to slow measurably for you. And if you speed up to 50% the speed of light, the effect becomes dramatic. At 90% the speed of light, time for you is passing at less than half the speed it does for someone standing still on Earth. And as you get closer and closer to 100% the speed of light, almost all of your speed budget is being spent on spatial movement, and almost nothing is left for you. Temporal movement, time for you practically stops. Your seconds correspond to years, decades, centuries for those left behind. And this is where the mathematics becomes truly terrifying. Let's do a thought experiment that Neil deGrasse Tyson loves to present in his lectures and programs. Imagine that you board a spacecraft capable of reaching 99.9% of the speed of light. You decide to make a round trip to the closest star to our Sun, Proxima Centauri, which is approximately 4.2 light-years away. At your near-luminal speed, the outward journey would take just over 4 years from the point of view of an observer on Earth, and the return another 4 years, totaling approximately 8 Earth years for the complete journey. But here's the cosmic trick. For you inside the ship, experiencing extreme time dilation, the entire journey would appear to last only a few weeks, perhaps a month or two at most. You would depart from Earth, make a journey that subjectively would seem relatively short. If you would visit another star system and return feeling like only one summer had passed, but when you landed, you would find that 8 years had passed on Earth. Your young children would now be teenagers. Your parents would have aged almost a decade. The world would have changed in ways you could not predict. And that's just for the nearest star traveling at 99.9% the speed of light. Now imagine longer trips or speeds even closer to the luminous limit. The mathematics of special relativity tells us that if you traveled at 99.99999% the speed of light, each day of yours would correspond to more than 2 Earth years. A 6-month journey for you would mean that more than 365 years have passed on Earth. You would depart leaving behind a 21st century civilization and return in a world completely unrecognizable from the 24th century or beyond. And the more nines you add after the decimal point, the more extreme the effect would be. Becomes infinitely approaching the speed of pure light. Time for the traveler approaches zero, while entire eons pass in the rest of the universe, which is why Neil deGrasse Tyson categorically states that everyone around you would be dead if you traveled at the speed of light. Not because something violent would happen to them, but because time would simply pass differently for you and them in such an extreme way that entire generations would be born, live and die while you experience only fleeting moments. And I want to hear from you. Now, where are you watching this video from? In which city or country are you currently contemplating these cosmic truths together with me? Comment below, because it is genuinely fascinating to think that people from all over the world are connected by this shared curiosity about the mysteries of the universe. We are all caught in the same flow. Temporal for now, but if any of us could travel at the speed of light, that connection would be destroyed forever by the gulf of time that would open up between us. Now, let's delve even deeper into this understanding, because there is a crucial question that many people ask when they hear about time dilation for the first time. If time passes slower for those who are moving, shouldn't the opposite also be true? From the traveler's perspective, it's not the Earth that is moving away from them. So shouldn't it be time on Earth that slows down? That's a brilliant question. And she takes us to the famous twin paradox, one of the most debated conceptual problems in the history of modern physics. Imagine two identical twins, let's call them Anna and Bruno. Anna decides to embark on a space mission, traveling at relativistic speeds, while Bruno remains on Earth. From Bruno's point of view, Anna is moving extremely fast, so Anna's time should pass more slowly. But from Anna's point of view inside the ship, she is not the one standing still, while the Earth and Bruno move away at extreme speeds. In this case, it shouldn't be Bruno's time that passes more slowly. When Anna returns, who will be older, the two reasonings seem equally valid and reach opposite conclusions. So, how do we resolve this paradox? The answer lies in the fundamental asymmetry of the situation. And this is where physics becomes even more elegant. Bruno remains in an inertial reference frame throughout the journey. He is floating on the Earth, which moves at essentially constant speed through space. Anna, on the other hand, needs to accelerate to leave the Earth, slow down when arriving at the destination, accelerate again to start the return, and slow down to land. She changes inertial reference frames multiple times during the trip, and this change of reference frame breaks the apparent symmetry of the problem. When you include the effects of acceleration, which Einstein later incorporated into general relativity, the mathematics makes it clear that Anna will be unequivocally younger when she returns. There is no real paradox, just an appearance of paradox that disappears when you analyze the situation fully. And this is not abstract theory. This has been proven experimentally in multiple ways throughout the last century. In 1971, physicists Joseph Haffel and Richard Keating carried out an elegant experiment that became known as the Haffel-Keating experiment. They took 4 cesium atomic clocks, the most accurate time-measuring instruments available at the time, placed 2 of them in commercial planes that flew around the world eastward, 2 others in planes that flew westward, and compared the results with atomic clocks that remained at the United States Naval Observatory. The results were exactly what relativity predicted. The clocks that traveled on the planes showed times slightly different from the stationary clocks, with differences of tens of nanoseconds perfectly calculable by Einstein's equations. Time had actually passed differently for the moving clocks, and since then increasingly precise experiments have confirmed time dilation with extraordinary accuracy. GPS satellites orbiting the Earth at speeds of approximately 14,000 kilometers per hour experience measurable time dilation. Their atomic clocks become. If we did not correct for this relativistic effect, the GPS system would accumulate positioning errors of approximately 10 kilometers per day, making it completely useless for navigation every time you use the GPS on your cell phone to find a restaurant or navigate to a friend's house. You are relying on relativistic corrections that compensate for time dilation. Einstein literally made modern navigation technology possible more than half a century before it was invented. And here is something even more surprising. Time dilation doesn't just affect mechanical or atomic clocks. It affects absolutely all physical processes. including the biological processes of your body. If you were traveling at 99% of the speed of light, your heartbeat would be slower from the point of view of an earthly observer. Your cells would divide more slowly. Your thoughts would flow more slowly. Your own metabolism would be slowed down. But you wouldn't notice any of this because your perception of time would also be slowed down by the same amount. For you, everything would seem completely normal. You would feel your heart beating at the usual pace. You would think at the usual speed. You would age at the pace you had always known. It's only when you compared your watch with that of someone you know, remained at normal speed, that the difference would become apparent. And this is precisely the existential horror that Neil deGrasse Tyson highlights. The light traveler feels nothing unusual. He simply lives his life on the ship as he travels through the cosmos. But when he returns, he discovers that he has lost not just years, but potentially his entire civilization to the temporal chasm that the speed has created. And if you are thinking of a way around this problem, I am sorry to inform you that physics is mercilessly consistent. Some people ask if we couldn't just maintain constant communication with Earth while traveling, sending video messages showing that we are fine and receiving updates about what is happening at home. And yes, theoretically, you could do that, but the communication would not solve the fundamental problem. It would only allow you to watch in near real time the people you love aging and dying while you remain young. Imagine sending a video message to your 10-year-old daughter and receiving a response from a 60-year-old woman who you barely recognize. Imagine watching via broadcast your parents age decades while you age only months. Imagine receiving the news of your birth of your great-grandchildren when you still feel in the vigor of youth. Communication would not eliminate the tragedy. It would only allow you to witness it in real time. Some people also ask about the possibility of taking their loved ones along on the trip, so everyone would experience the same time dilation, and no one would be left behind. And in fact, this would be a partial solution. If your whole family boarded together on the same ship traveling at the same speed, you would all age together at the same slowed pace. But that would only change the scale problem. You would escape together from Earth's time. But upon returning, you would discover that everything and everyone who didn't come along with you has disappeared in the mists of time. The civilization you left, the friends who didn't come, the culture you grew up in, everything would have transformed or disappeared. You would be eternal foreigners in time, visitors from a past that no one else remembers. And this leads us to a deep philosophical reflection that Neil deGrasse Tyson often explores in his discussions on interstellar space travel. The speed of light is not just a technical barrier to space travel, it is an existential barrier that fundamentally isolates travelers from their origins. Even if we developed technology to travel at speeds close to light, which would be necessary for any practical form of interstellar exploration, given the vast distances involved, any astronaut who set out on such missions would essentially be permanently exiling themselves from their own time. They could explore distant stars, discover alien planets, perhaps even encounter extraterrestrial life. But they could never share their discoveries with the people who inspired them to leave. They could never return to the world they knew. The universe is vast too much, and time is too relentless to allow light travelers to maintain connections with their origins. And if you are finding these revelations as impressive as I did when I first studied them, please like this video because it really helps the channel grow and motivates me to continue producing in-depth scientific content like this. And if you haven't subscribed yet, this is the perfect time, because we have many more fascinating explorations of the cosmos planned that you won't want to miss. Now let's look at another crucial aspect of this physics that many people don't. Consider what exactly happens when you approach the speed of light, not just with time, but with space itself and the mass of the moving object. Because time dilation is just one part of a set of relativistic transformations that Einstein discovered, and they all conspire to make travel at the speed of light literally impossible for any object with mass. Let's start with length contraction, also known as Lorentz contraction after the Dutch physicist Hendrik Lorentz, who first mathematically described this phenomenon. When an object moves at relativistic speeds, it literally contracts in the direction of motion. From the point of view of a stationary observer, at 90% the speed of light, an object would appear compressed to less than half its original length. At 99.9% the speed of light, a 1-meter object would appear to be only a few centimeters long, and as the speed approaches 100% of light, the observed length approaches zero. The object would appear to flatten until it becomes two-dimensional. It is clear that from the point of view of those inside the objectus in motion, everything appears normal. It is the rest of the universe that appears contracted in the direction of motion. Distances ahead appear smaller. Objects appear flattened, and this is in fact one of the mechanisms that allows interstellar travel in reduced subjective time. Not only does time pass more slowly to the traveler, but the distances themselves appear smaller from his point of view. A trip to a star, 100 light-years away, could appear to be only a few light-years long to a traveler moving at extremely fast speeds. In relativistic ways, combining time dilation and length contraction, travel that is impossible in terms of terrestrial time becomes conceivable in the traveler's subjective time. But this does not solve the fundamental problem of temporal disconnection. It only makes it more pronounced. Because while the traveler experiences a relatively short journey through an apparently contracted space, entire eons pass in the uncontracted universe around him. But perhaps the most fundamental obstacle to achieving the speed of light is the relativistic increase in mass. And here physics becomes truly unforgiving. As an object with mass accelerates toward the speed of light, its effective mass increases. The additional kinetic energy you are pumping into the object begins to manifest itself as additional mass rather than additional speed. At 90% the speed of light, an object has approximately twice the mass it had at rest. At 99%, its mass is about 7 times greater. At 99.9%, approximately 22 times greater. And as you get closer and closer from 100% the speed of light, mass grows towards infinity. This means that the energy required to accelerate also grows towards infinity. There is literally not enough energy in the observable universe to accelerate even a single electron to exactly 100% the speed of light. The speed of light is an absolute limit, a cosmic barrier that cannot be crossed by any object that has mass. No matter how much energy you have available, no matter how advanced your technology, the laws of physics themselves prohibit massive objects reach this speed. And so photons of light, which have no rest mass, can only exist at the speed of light. They are born traveling at 300,000 kilometers per second, and they die still traveling at 300,000 kilometers per second. They never accelerate. They never slow down. They simply exist at that speed, or they do not exist at all. And here is something truly mind-blowing that Neil deGrasse Tyson often highlights. From the point of view of a photon of light, time does not exist. Like the speed of the photon is exactly the speed of light. Time dilation is complete and absolute. Time for the photon is completely stopped. A photon emitted by the Big Bang approximately 13,800,000,000 years ago has not experienced any time since its creation. From its own point of view, the moment of its creation and the present moment are simultaneous. Even more extraordinary, due to extreme length contraction, the entire universe is flattened to 0 dimensions in the photon's direction of travel. The distance between its starting point and its of arrival is literally 0 from your point of view. The photon does not travel through space-time. It simply instantly connects 2 points that, from your point of view, are the same point. Of course, we massive observers see the photon traveling for billions of years through billions of light-years of space. But the photon itself experiences neither time nor distance. This is one of the strangest and most counterintuitive consequences of special relativity, and demonstrates how radically different the experience of reality is for entities that travel at the speed of light versus massive entities like us. And this brings us to a question that a lot of people have when they hear about these relativistic limits. If we can't reach the speed of light, how close can we get? And what are the practical effects as we get closer to that limit? The answer is that theoretically we can get arbitrarily close. We can get 90%, 99%, 99.9%, 99.99%, and so on. Onwards, each additional 9 requires exponentially more energy, but there is no hard limit before 100%. We can get as close as our technology and energy resources allow. We just can't get there completely, and the effects as we get closer are progressively more extreme. At 90% the speed of light, time passes approximately 2.3 times slower for the traveler, a 23 journey. Earth years would feel like just 10 years to those on the ship. At 99%, time passes approximately 7 times slower. A journey of 70 Earth years would feel like just 10 subjective years. At 99.9%, time passes approximately 22 times slower. A journey of 220 Earth years would feel like just a decade. And at 99.9%, time passes approximately 70 times slower. Slowly, a 700-year journey would correspond to just 10 years of aging for the traveler. You can see how quickly the effects become devastating to any human connection between the traveler and those left behind. Even speeds that are technically far below light in percentage terms create temporal chasms of decades and centuries. And I want to pause here to ask which aspect of this physics you find most disturbing. The fact that time is relative and not absolute, the impossibility of maintaining connections across relativistic speeds, or the idea that photons of light do not experience time or space. Comment below which of these revelations impacted your view of reality the most, because I am genuinely curious about how different people react to these cosmic truths. Now let's explore what this all means for the future of human space exploration. Because these are not just theoretical curiosities. They are fundamental limitations that any space civilization will have to confront. The closest stars to our Sun are light-years away, Proxima Centauri 4.2 light-years, Sirius at 8.6 light-years, Tau Ceti at approximately 12 light-years, even traveling at a significant fraction of the speed of light. Reaching any of these stars would represent a journey of years or decades. And the further you want to go, the more extreme the requirements become. The center of our galaxy is approximately 26,000 light-years away. The Andromeda Galaxy, our closest galactic neighbor, is 2.5 million light-years. At conventional speeds, even a fraction of a percent of the speed of light. These distances represent thousands or millions of years of travel, completely outside any conceivable human scale. The only way to make intergalactic or even distant interstellar exploration remotely viable in terms of subjective time would be through extremely relativistic speeds. But as we have seen, this would create an insurmountable temporal gulf between the travelers and any originating civilization. Departing astronauts to explore the galaxy, they would no longer be members of any terrestrial society. They would be completely separate entities, time travelers who could only move forward, never return to their own period. And this has profound implications for how we imagine advanced space civilizations. Much science fiction imagines unified galactic empires, federations of planets spanning thousands of star systems, interstellar communication, and commerce. But relativistic physics makes all of this extremely problematic. Even communication at the speed of light would take years or decades between nearby star systems, centuries or millennia between distant regions of the galaxy. How would you maintain a unified civilization when a message takes 1,000 years to reach the recipient and another 1,000 years for the response to return? Any galactic empire would necessarily be a collection of autonomous entities that long ago diverged from any common ancestor, not a functional federation with centralized government, and physical travel would be even more isolating than communication. Envoys leaving, carrying messages, or delegations would arrive at their destinations centuries after they left, finding civilizations completely transformed or even extinct. The person who sent them sent, and the message they carried would be relics of a distant past, irrelevant to current conditions. Some physicists and philosophers argue that this limitation may be the answer to the Fermi paradox, the question of why we do not see evidence of alien civilizations in such a vast and ancient universe. Perhaps intelligent civilizations arise frequently, but the vastness of space combined with relativistic limitations makes galactic expansion practically impossible. Each civilization remains isolated in its immediate stellar neighborhood, unable to project significant influence beyond a few tens of light years away. The universe may be filled with islands of intelligence, separated by oceans of space-time that are effectively impassable, not because travel is physically impossible, but because time takes too high a toll. No civilization can maintain coherence across distances that require centuries or millennia of travel. Even in subjective time, you can send colonists to distant stars, but when they arrive, they will have become something completely different from the civilization that launched them. And you will never know what happened to them because their reports would take other generations to return. Other people question whether there are ways around these relativistic limitations. And in fact, theoretical physics proposes some concepts that could theoretically allow faster-than-light travel, although each comes with its own monumental problems. The most famous is probably the engin d'Alcubierre, proposed by Mexican physicist Miguel Alcubierre in 1994. The idea is elegant. Instead of accelerating a ship through space, you contract the space in front of the ship and expand the space behind it. The ship remains stationary within a bubble of normal space, but this bubble moves through the surrounding space at speeds potentially much greater than light. As the ship is not actually moving through local space, it does not violate the relativistic prohibition against moving faster than light. Light, relativity, only prohibits local motion faster than light. It does not prohibit space itself from moving in creative ways. And if this seems like a semantic trick, well, in a way it is, but it is a semantic trick that the mathematics of general relativity seems to allow. The problem is that making this work requires absurd amounts of negative energy, an exotic form of energy that may not exist in macroscopic quantities or that may be completely impossible to create. Original calculations suggested that you would need more negative energy than the total mass energy of the observable universe to create a working Alcubierre bubble. Later refinements have reduced this to something more reasonable, perhaps the mass energy of Jupiter. But even this is completely beyond any conceivable technological capability. And there are other problems. The Alcubierre bubble would create intense Hawking radiation that would likely destroy anything inside it and cause devastation upon reaching the destination. It is also not clear how you would slow down the bubble or even how you would create it in the first place. Instead, physics allows the bubble to exist, but offers no clear mechanism for creating or controlling it. Another concept that often appears in discussions of faster-than-light travel are wormholes, hypothetical connections through space-time that could create shortcuts between distant regions of the universe. The idea is that instead of traveling the full distance between two stars through normal space, you would enter a wormhole and emerge on the other side instantly or nearly instantaneously. General relativity allows for the existence of wormholes mathematically, but again, the practical problems are immense. Natural wormholes, if they existed, would probably be microscopic and extremely unstable, collapsing in infinitesimal fractions of a second. Keeping them open long enough to get through would require, again, negative energy or exotic matter. And we have no evidence that wormholes exist anywhere in the observable universe. And here's the most disturbing problem with any form of faster-than-light travel. If you can traveling faster than light, you can potentially create temporal paradoxes, going back in time and arriving before you have left. This creates possibilities such as killing your own grandfather before your father was born, the famous grandfather paradox, or sending information to your past self that would alter the decisions that led to sending the information. Most physicists believe that such paradoxes are impossible, that the universe does not allow contradictory causal loops. And if this is true, then any mechanism that appears to allow faster-than-light travel must fail in some way. There must be some physical obstacle that we do not yet understand that prevents the creation of time machines. Stephen Hawking proposed the chronological protection conjecture, the idea that the laws of physics conspire to prevent time machines even when the equations seem to allow for their theoretical existence. The universe appears to have guards against causal paradoxes built into its fundamental structure. And this would mean that faster-than-light travel is probably impossible for reasons deeper than simply not having enough technology. It may be fundamentally prohibited by the causal structure of the cosmos. Neil deGrasse Tyson often observes that we must have humility about what is possible, but also realism about the obstacles. Perhaps civilizations much more advanced than ours have found ways around these limitations that we simply cannot conceive of, just as a medieval human could not conceive. Instant communication via electromagnetic waves or images transmitted through the air. But it is also possible that some limitations are truly fundamental, that no matter how far a civilization advances, there are things that simply cannot be done because they violate the most basic laws of physics, and the speed of light as a limit may be one of them. What this means for us as a species, it means that if we want to become a spacefaring civilization, we need to embrace the vastness of time just as we embrace the vastness of space. Generational ships that travel for centuries, civilizations that fragment into isolated groups, each following their own evolutionary path. Communication that happens on scales of decades or centuries. A humanity not as a unified species, but as a diaspora of divergent lineages spread across the stars. This may seem depressing from a certain point of view, the loss of connection, the impossibility of a common home, but there is another way of looking at it. If this is the best that physics allows, then it is simply the reality that any intelligent civilization must work with, and there are ways of finding meaning and purpose. Even within these limitations, each generational ship would be a complete civilization unto itself. Each star colony would develop its own culture, art, science, and philosophy. The diversity of conscious experience would expand enormously, even if communication between these experiences were impossible or extremely delayed, and perhaps that is enough. Perhaps exploration need not be about connecting everything into a unified network. Perhaps it is about sowing seeds of consciousness in all directions and letting each seed blossom in its own unique way. We will not personally know what our distant descendants will become, but we can know that we contributed to its existence, that we launched the stream of life and consciousness toward the stars. Even though we knew we would never see where it would go, there is a certain beauty in this way of thinking about space exploration, and Neil deGrasse Tyson often emphasizes that the cosmos owes us nothing, should not be navigable on convenient human scales, should not allow us to maintain connections across interstellar distances. It simply is what it is, with its merciless and indifferent laws, and our task is to find ways to flourish within those laws, not to complain that they are not as we would like. And if you have made it this far, in this exploration of the deepest truths about speed, time, and space, I want you to know that this means a lot to me. It means that you are exactly the kind of person I create this content for. Someone who does not shy away from complexity, who embraces the discomfort of having their intuitions challenged, who prefers difficult truths to comfortable illusions. So if you haven't subscribed to the channel yet, now is the time. And if you have already subscribed, share this video with someone you think would enjoy this intellectual journey. Together, we are building a community of people who face the cosmos head-on. Without blinking, let's continue exploring some more implications of these relativistic truths, because there are aspects we haven't fully covered yet. A question that comes up often is about what happens to consciousness during relativistic travel. If time passes slower for you as you travel, is your mind running slower? Are you thinking slower, experiencing less? The answer is no. From your own point of view, everything works normally. You think at normal speed, you experience time flowing at normal speed. There is no way to look at a clock inside your ship and determine that you are moving at relativistic speeds. Everything inside the ship seems perfectly ordinary. It is only in comparison to the rest of the universe that the difference manifests itself. And this raises interesting philosophical questions about the nature of time and consciousness. Whether your subjective experience is identical in both scenarios, traveling or standing still, in what sense time actually passed differently for you? Physics tells us that your body aged less, that fewer events occurred to you, but your experience of temporal passage was identical. This suggests that time is not a single, universal thing, but rather a local property that depends on your state of motion and gravitational position. Each point in space-time has its own local time, and these local times may be at odds with each other. There is no universal now, a cosmic present shared by the entire universe. Events that are simultaneous for one observer may not be simultaneous for another moving observer different. The very concept of simultaneity is relative. Einstein demonstrated this through a famous mental experiment. Imagine that you are in the middle of a moving train, and two rays fall simultaneously at both ends of the train. You are exactly in the middle, and the light from both rays reaches you at the same instant. So from your point of view, the rays were simultaneous. But imagine someone standing on the platform observing the same event as the train is moving. You are moving towards the light coming from the front of the train and away from the light coming from the back. So to the observer on the platform, you received the light from the front before the light from the back. And if the rays were adjusted so that the light arrived simultaneously at you, so the rays did not fall simultaneously from the point of view of the person on the platform. The ray behind had to fall first to compensate for its movement towards the front. Who is right? You who saw the rays as simultaneous, or the person on the platform who saw one before the other? Einstein's revolutionary answer is that both are equally right. There is no such thing as absolute simultaneity. Different observers in different states of motion legitimately disagree about the order of events, and neither is more correct than the other. This has implications. This means that the past, present, and future are not absolute divisions of reality, but depend on the observer. Events that are future to you now may already be past to an observer moving differently in a distant region of space. The entire geometry of time is much stranger than our everyday intuition suggests, and it is within this conceptual setting that relativistic travel occurs. When you accelerate to near-light speeds, you are not just moving faster through space, you are reorienting your trajectory through space-time in ways that fundamentally change your relationship with the rest of the universe. The events that were your future are being redistributed. The temporal relations between you and everything else are being reconfigured. And it is this reconfiguration that results in you returning to find everyone you ever loved dead. You have not traveled to the future in the science fiction sense. You have simply followed a trajectory through space-time that has accumulated less time of its own than more conventional trajectories. But the practical result is indistinguishable from future travel. You emerge from the flight to discover that the world has advanced much further than that you is one-way travel to the future, with no possibility of return. Some people ask if this makes relativistic travel a form of relative immortality. After all, if you could simply continue traveling indefinitely at speeds close to light, you would age very slowly in relation to the rest of the universe. Thousands of Earth years could correspond to just decades of your subjective life, and in a sense this is true. You could see civilizations be born and die while you age just a few years, but it would be an extremely lonely immortality. Each time you stop to observe the universe, everything you knew would be gone. You would forever be a stranger, a visitor from increasingly distant pasts in increasingly alien futures. There is a science fiction tale called Tau Zero by Poul Anderson that explores this idea. A ship with a deceleration malfunction that continues accelerating indefinitely. Approaching ever closer to the speed of light, the crew watches as its time dilation becomes so extreme that galaxies are born and die in instants of subjective time. Eventually, they witness the end of the universe itself and the birth of another, all in a few hours of in-flight time. Is a fascinating exploration of the extreme philosophical consequences of time dilation, although obviously fanciful in terms of actual possibility. But it illustrates how fundamentally strange the universe becomes when you take relativity to its logical conclusions. And it brings me to the final reflection on what Neil deGrasse Tyson and other astrophysicists want us to understand. When they explain these truths about the speed of light and time, it's not to depress us about impossibilities. It's to expand our understanding how magnificent and strange the cosmos really is. We grow up with intuitions about time and space that work perfectly well for everyday life on the surface of a planet, moving at speeds far below that of light. But these intuitions are approximations of a much stranger and more wonderful reality. Time is not the constant universal flow it appears to be. It is elastic, flexible, relative, different to different observers. Space is not the empty, unchanging arena it appears to be. It curves in the presence of mass. It can expand faster, that light can potentially be connected in exotic ways that we do not yet fully understand. And the speed of light is not an arbitrary limit imposed by the universe. It is a fundamental consequence of how space-time works. Ona, a signature of the deepest laws of physics, understanding this does not diminish us. It magnifies us. We are creatures that evolved on a small rocky planet around an ordinary star, using brains that evolved to track prey and find mates. And yet, we can discover these cosmic truths. We can see through our limited intuitions to the underlying reality. We can mathematize the behavior of space-time in situations that we could never experience directly. This is extraordinary. It is perhaps the most extraordinary thing our species has done. Has already done. And when we contemplate the limitations that physics imposes on space travel, we must do so with awe at the fact that we discovered these limitations. Before Einstein, we didn't even know there was a cosmic speed limit. Before relativity, we couldn't even correctly formulate the questions about what would happen at speeds close to light. Now we know. We know with mathematical precision and experimental confirmation what would happen. We know exactly why we would return to find everyone dead. We know the equations that govern time dilation and length contraction. We know why that the speed of light is fundamental and unattainable. This knowledge is a form of power, not power over the universe. It will continue to function as it always has regardless of our desires, but power over our own understanding, freedom from ignorance, the ability to see the cosmos as it really is rather than as our intuition insists it should be. And this is what astrophysicists like Neil deGrasse Tyson are trying to share when they explain these truths. Not a list of things we cannot do, but a window into how profoundly strange and wonderful the universe that we have the privilege of trying to understand. So the next time you look at the stars at night, remember that the light that is entering your eyes has traveled for years, decades, centuries, or millennia to reach you. But from the point of view of that light, no time has passed, it left that distant star and reached your eye instantly. You are connected to the stars through photons that have not experienced time, through light signals that for them link past and present without gap. The universe is much stranger and much more connected than it seems. And if we could travel at the speed of light to visit these stars in person, we would pay a terrible price in terms of human connection. Everyone we loved would be dead when we returned, but we would have seen the cosmos in ways no human has ever seen. We would have experienced the paradox of flexible time directly. We would have become travelers not just of space, but of time itself. And there is something immensely poetic about that, even if it is also tragic. And if this video expanded your mind as much as it expanded mine when I first studied these concepts, leave a like, subscribe to the channel, hit the notification bell because we have so many more explorations of the cosmos planned, so many more weird and wonderful truths to share, so many more frontiers of knowledge to explore together. The universe is vast and strange and magnificent, and we've barely begun to scratch the surface of it. Thank you for traveling with me on this intellectual journey through time and space, through Einstein's equations and the reflections of deGrasse Tyson, through the deeper implications of what it means to live in a cosmos where time is relative and the speed of light is absolute, where travel between stars is possible but comes at a price we may not be willing to pay, where the greatness of the universe is matched only by the strangeness of its fundamental laws. This is the cosmos we live in, not the cosmos we would wish, but the cosmos that is. And there is beauty in learning to appreciate it on its own terms, instead of lamenting that it is no different. Until the next exploration, keep looking at the stars and wondering about the mysteries they hold, because it is this curiosity that drives us, makes humans, and that can eventually lead us to them, even if the path is much stranger than we ever imagined.